Okay. Hey, okay. Uh, in the last lecture, which is the first lecture in this series, we just discussed about the overview of the recent classical and quantum machine learning algorithm in high energy physics, and then we mostly covered all the classical machine learning algorithms, and then we stopped or we briefly discussed about the quantum machine learning algorithm. So before we go and jump into the second lecture, which is about introduction, a basic introduction about machine learning, linear and nonlinear regression models, then we may give some a little bit details about what we lived in last night. Okay, so starting with this, again, how can we construct a quantum machine learning or a machine learning algorithm on a quantum computers? And we know that there are like 2-3 steps. The first one is that we need first to prepare all the qubits in the zero state, and the reason for that, we actually, if you are a bit curious, then you might go to the slide or the last lecture, then you can look for this. But we just prepare all the qubits between the zero states, and then we embed actually the classical data on the qubits, like we want to map them, we want to put them into the qubits, and then we do as far as we embed or encode our classical data on quantum computers, then we are in a quantum system, and our classical data lives in a Hilbert space, and then we actually are able to do more unitary operations and unitary transformation on the embedded data. And once we do this unitary operation on the data, as you can see, these unitary operations are a function of some free parameters data, right? So those are the free parameters that we tune to approximate the function f. So if you remember that the main goal of any machine learning algorithm is to approximate the function f that maps the data x, classical data x, to the domain y. So to do so, actually, these hyperparameters or these free parameters take the roof of that. So every time we try to tune or try to update and optimize the values of these data parameters such that the output or the measurements from the quantum circuit can approximately fit the function or the required function. And as far as we hear, then we can do some measurements, and the measurements actually is done by having some a Pauli Z operator, right? So you know about the Pauli matrices, right? So we have Pauli X, Y, and Z, and the eigenvalue of those are 1 or -1, and then we could have some calculate some error function. Like we have the label, for example. If it belongs to the first category or the first class, then I can map this or label this by label 1. If it belongs to the second class, then I can label this by -1. And when I do the predictions, then I can find the error function, like the predicted value minus the true value, and then I try to update again and again until the error is minimized. Well, so I also saw these plots, and there are different parameterization here, at angle embedding, amplitude embedding, and radiated embedding, and we end up with like 2 features for the quantum machine learning over the classical one. The first one is that the quantum machine learning actually learns from very few data. So there is no need for very, very large data to learn the hidden feature inside the data. In quantum machine learning, we don't need that.
And also, what makes the repeated embedding perform better than all the other embedding and the construction of the circuits, and this is because of that. So if you keep repeat the embedding of the data on your variational quantum circuits, that is considered as a heterogeometric sum of different sine and cosine function. So if you, for example, the first embedding is the very nice sine function like this, then you add more different one with different frequency, different amplitude, and you add more and more, then you find at the end how your function looks like, right? So then having actually this kind of forbidden embedding can easily approximate any continuous function, whatever the complication of this function is. Okay, and now the question is, can we construct a variational quantum classifier with only one qubit? And the answer was yes, we can do that. And of course, we have some comparison using the universal approximation theorem. And this universal approximation theorem, it first originated to explain how the neural network with only one hidden layer can explain and can approximate any function, no matter how complicated the function is, right? And then we explain how this takes place, right? Well, so this is an example, and you can find this example here in the website of the Pennyland, which is powered by Xanadu company. So you can go there and try this yourself. So we have actually a two-dimensional data, and this data has two classes, like the blue class and the red class. And this data is, as you can see, obviously it's nonlinear separable data, right? So we cannot find a line that can separate between the blue and red data, right? So we need to use only one qubit to classify this. So we first have the qubits, we prepare the qubits into their states, and then we embed the qubits using the angle rotation. So we rotate the qubits with the value of the x, and then we do some unitary operation on it, like also another rotation using the free parameter of theta 1, and then we keep repeating the blocks as far as we can, and at the end we do the measurements. Once we do the measurements, then we can compute or calculate the cost function. And the cost function actually is 1 minus the fidelity. And after we minimize the cost function, then you can find the prediction of the model. When we train the model on 2000 points, with it can evolve, like it can iteration every time we try to optimize and tune the free parameters, the theta free parameters. And this is before any training, so this is the actual data actually, as you can see here, right? So this is, we expect if the model is able to give it any new unseen data and then predict the shape, then this is 100% accuracy that the model actually achieve the approximation of the function. So this is the true data, and before any training for the model, you see the blue and red points are randomly scattered everywhere on the helper space of the qubits. But after training for 10 epochs, then you can see how nicely the model is able to understand and learn non-linear classification boundaries that can separate between the two classes. But the question now is how these circuits, very simple circuits, how these circuits actually learn and optimize the data to learn this better, right? So there is one thing that we miss here, which is the fidelity, or the quantum fidelity. So what's the quantum fidelity? This, the quantum fidelity, actually, it measures the inner product between the two states. So it means that it measures the similarity between the two states, right? Because at the end you find that it's cosine angle. So as far as the cosine is 0, that means two states are similar or different. And in classical machine learning, actually, we have the cosine similarity, and we are going to see that. So this fidelity, or 1 minus the fidelity of the two states, is actually a metric distance cost function. So you can measure how close the two states are. So as far as we minimize 1 minus the fidelity, that means we make the predicted states and the true states to be very, very close together and even identical. So the idea here is that 1 minus fidelity is a metric distance. So what is the advantage of metric distances? Metric distances, or using this distance as a cost function? Well, so as you can see here, before any training, everything is randomly scattered, right? And this is how the data is mapped on the qubits, on the hyperspace of the qubits. So at the beginning, it's random. So everything is mapped randomly, right? But after training, we try to minimize 1 minus the fidelity. That means we try to push the blue data on one of the states and push the other completely far away on the other states. So this is exactly a metric, because it's, as you can see, it's a distance between them. So we try to increase the distance between the two states by minimizing 1 minus fidelity, and fidelity is nothing but the similarity between the predicted state and the target state. Well, so okay, as we discussed yesterday about the problem with the noisy intermediate quantum computers, and at the moment there is no clear advantage of the quantum computers over the classical computation, but there is another novel solution, which is a hybrid classical quantum algorithm or model. So how these kind of things work? So we first start, like for example, if we want to analyze image, right? And this image has something like so the dimension of the image, right? It has 225 times 225 times 3, where 3 is the depth of the image, right? So if you want to embed this image on a quantum computers, then you have to embed each pixel on 1 qubit, right? So how many qubits? It's 2 times 3. So this is impossible, right? So we need this number of qubits, and this is impossible. So one way to do that is to use a classical machine learning model, such that it takes the image, and as we discussed, or you saw yesterday also, this kind of convolutional neural network, it reduced the dimension of the image to some data in space. As far as here, we reduce the dimensions, and then we can use the mapped image, or the mapped characteristic information or hidden information into the image to be analyzed with the quantum circuits. And for that, we have 2 setups actually. The first one is that after we make the measurements from the quantum circuits, we can update the weights, like the quantum weights, and also the classical weights, or the weights for the classical algorithm, or the classical convolutional neural network, or we can train only the classical part alone to map the data to some data in space, and then we freeze the weights. So during the optimization or each iteration, we update only the weights for the quantum circuits apart from the classical one, right? And actually, we tried both, and there is no much difference. But there are 2 options actually that we can try. Well, so this is an example of what I was discussing. So we have a set, and this is called a Fashion Eminence data set. That's a very popular data set in machine learning. And you can see the dimension of the image is 28 times 28 times 1, because this is a gray image, a binary image. So it's not colored. And we want actually to construct a hybrid classical model to actually distinguish the trouser from the shirt images. As you can see, this is part of the code. I'm going to show you how these kind of things work. But the most important thing is that here, this is the quantum layer that we have. And then, as you can see, I'm not sure if this is clear or not, but you can see here, we start with 28 times 28 times 1. So this is the dimension of the image, right? So this is the 28 times 28 times 1, depth of the image, because this is a gray image. And as far as we do convolution and operation, you can see the dimension of the image is keep reducing until we end here to 6 times 6, and even less to 3 times 3. And as far as we have the dimension of 3, like I compose the information here, the given information of the image to only one vector of dimension 3, then we can use one qubit, because the optimal information that one qubit, or the degrees of freedom, maximal degrees of freedom that this one qubit can have is only 3, right? Like the rotation of the 3 axes. So to use one qubit, we need actually to. Sorry.
What are the 3 degrees of freedom?
The rotation on the 3 axes, like the x rotation, y rotation, and z rotation.
Wouldn't those be 2?
Sorry.
Wouldn't those be 2?
Because it's a qubit is represented on a clock speed.
Sorry.
We represent a qubit on a clock speed.
Yes.
Isn't those just 2 degrees of freedom?
No, there are 3, because at the end, look. That's a good question. So at the end, we keep summing them this one. So there is a phase exists. So at the end, you still have a phase, and these are 3. Not 2. So you have 2 angles, depth, and one phase. So at the end, you sum to 3 information, 3 degrees of freedom.
Overall phase? Do you mean an overall phase?
Yes. Not the overall phase, because here you sum of each phase. So you have U1 plus U2 space, U1 plus U2 space. You cannot factor out. No, but this is a good question, by the way. Okay. Here, this is the fidelity as a classifier, and the fidelity actually ranges from -1 to 1. And as you can see, the test 1 is basically the predicted data for shirts, and the test 0 is the predicted data for trousers. That means that all the t-shirts or the shirts images has been gathered toward the state 1, and the other images for the trousers have been accumulated to the state 0. And these are the classical linear space, like the distribution here, and this in this classical linear space, and this is how it looks like. But as you can see, the test accuracy is nothing but 86%, right? Which is
I'm just finding
and its train accuracy is around 93.
I mean, so there are things, superpositions between shirts and trousers and so on. You don't know whether it's let me see.
That's very things.
Okay.
Okay, so still the accuracy is not that good, right? We are looking for more. But now look at the problem is that as far as we do a unitary transformation, then we have the 2 pi, right? So this is the rotation. So if you rotate again with 2 pi, then you are the same. So we have to keep this in account, take this into account. And also if you use
This is a gauge shirt.
Yes, that's true.
These
Yes.
know there is currents. And
Yes, this is how we link.
So this
Yes,
is,
this is how we link lectures.
So this is invariant
under this one.
Derivative?
No. This is not invariant. It makes a lot of problems. So we have to
So
normalize
you should
it.
explain this.
and also if you have an amplitude embedding, so the amplitude embedding, you can explain your wave function as like, for example, the size state is alpha 1 plus the state 0 of state 0 plus alpha 2 state 1, and these are counter probabilities, and this has to be normalized to 1. So if you use also the amplitude embedding, then you have to normalize your inverse to be 1. But here this is no longer the case. And now we look, once we use a function called unit norm to normalize the inverse to the quantum circuits, then you can see how the jump of the test accuracy now. So now instead of 86, now we have a 93 accuracy, which is pretty good for 1 qubit. Okay, so that's all, and then let's go to the second lecture. Yes, please.
التريننج accuracy مقصود بيها ايش؟ تريننج ان انا بديله الصور واقول له دي كذا ودي كذا
I
فهو
will
يتعلم
answer.
منها.
I will answer you. Don't worry.
Yeah, part is what? Okay, good. Okay. 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 So the first part was about some advanced concepts and how to use some advanced machine learning techniques in high energy physics. Starting from here, we start from the basics of the machine learning. Good. So before we go on, we need to unify some of the notations and learn what is the difference between different concepts that we are frequently hear when dealing with the machine learning stuff. So there are a lots of, this is very, very popular and very famous chart to make some differences between what's called artificial intelligence and the machine learning, deep learning, and also some neural network. Well, so the artificial intelligence is all these kinds of some little bit smart programming, and even if you try to do some statistical model and you keep just putting with some with some programming language, this is kind of artificial intelligence. But from here, we have even a very smaller concept which also depends on the statistics background and all the mathematics. And this is machine learning, but in this case, we ask the machine to help us. So we learn some stuff, or we ask the machine to learn some information that at the end we can learn from this information. And this circuit actually is very, very wide. And there are some shallow algorithms like linear and logistic regression. This too we are going to discuss today. And also it has some simple algorithms like the k-means, supported vector machine, and all these kind of things. And those algorithms actually, they do not need what's called backpropagation or increase in the number of the hidden layers. So they are very shallow algorithms that they are designed actually to solve a very specific, simple problems. But at the end, to solve these problems, we need a machine, right? So we need a machine to learn some properties of the data, and then it can help us. Another or a smaller concept of that was called the deep neural networks, or the neural networks. So in the neural networks, we have the concept of the layer and the concept of the hidden layers. So we have a layer, and this layer consists of different neurons, and those neurons are actually connected to each other. It's exactly like some simple brain, a human brain that can think with you. And the deep one, or the most advanced one, what's called the deep learning. So by deep learning is that as far as you increase the depth, like how many deep layers you include or hidden layer you include in your network, this is considered as the deep or the depth of your model.
What does hidden layer mean?
The hidden layers, this is the structure of the model.
Yes.
Like, so it's like this one, like we have the first, these are the neurons, right? And each neuron here takes some input data like x1, x2, and x3, and so on. This is the input layer. This is called input layer, right? And then the weights of this has to be connected to another layer with different neurons, like fully connected, right? And everything is connected to each other. And then we have the output layer, which is, for example, like if you need to distinguish two classes, then there are only two layers, two neurons, right? And these neurons carry the probability either your input data belongs to the first class or to the second class. The point is the following: as far as you increase the number of this layer, you repeat these layers with different sizes, then you have different weights that can be tuned such that the deep model can learn more information than the shallow.
What is a shallow one then?
It's only,
That's-
it's only one layer.
Ah,
That's the point.
okay, so there are more layers.
Yes. So as more as you keep adding hidden layers, the more of the freedom that you add to the model to approximate and learn. More complicated structure.
Yeah, more parameters, basically.
Exactly. Exactly. Okay. So again, let me remind you with the answer by ChatGPT, and just like my humble opinion and my humble advice that you should have used that one. So this is kind of magic. Then you have to get the advantage from the magic. So when I ask, just a reminder again from the ChatGPT, and the answer, when I ask him about what is machine learning algorithm, just in one sentence, and the answer with that, it's mathematical instructions that enable computer to learn pattern from data and make predictions. So there are three things, right? Mathematics, pattern in the data, like how the behavior of the data, how the data looks like. And once the computer learns this pattern from the data, we can use it to make a predictions for new unseen data. Well, so very neat example how the machine learning looks like. So actually any machine learning algorithm is like a kid. It's a baby actually, and you try to learn it. So how to teach
I just
it?
want to make a note
Yes.
that there is a book by Cox and Miller from 1950 something, where they talk about Gaussian models for regression, where they make a similar statement.
Oh, good.
About how you can predict
Yes,
how
yes.
a random Gaussian
Yeah.
models predict.
Yeah, maybe ChatGPT learned from that book actually.
That's the point.
That's
That's my point.
Yes. Okay, so you can think of the any machine learning model as a kid. It's your baby, and once you have a baby, then there is no thoughts inside, no instruction, nothing. So you try to give the baby the instructions, and you try to teach the baby different things actually. So for that, before that, the machine learning actually consists of two parts. The first one is that training, right? You teach the model. You try to make or give information to the machine such that the machine understands what's going on. And after you teach and make the training step, then it comes the test step. When the test is the following, once the exam at the end of the semester, right? So you keep taking information the whole semester, and then at the end the tutor just ask for exam, and then your evaluation, like your understanding on about the instructions or about the material that you have. Example that I have a kid actually. I have two, they are twins, and when I try to teach them how to do the sum, so I get them in like exactly the same column like that, and then I said, okay, 1 plus 1 equals 2, 1 plus 2 equals 3, and so on, etc., until 1 plus 9 equals 10. So from this, my kid actually learn and understand the logic of the plus, right? So whenever he has this one, then he understand the logic. So he sum in his fingers the first number plus the second number. And now after they learn the logic of the sum, I give him a little bit different number, right? So I said, okay, 2 plus 5, what that equals. So that's the point. But just keep in mind, when we test on the logical operation that we want the model to learn. Like for example, if you train your model to learn the function f, which is in our case is the plus or the sum, and now you ask him ask the model, and now you ask him 2 times 5. Of course, it would be wrong answer, right? Because he understands only one function, which is the plus or the summation function. So that's the point. So we train the model on some data, and then we change the data. So these two data, the model actually never seen them, like 2 and 5, but same operation, right? Okay, so apart from the kids, let's remove that to the machine. And of course, the machine now, it can analyze a high-dimensional data like images, for example. And now I train the model actually to learn the characteristic features
and the different features between cat and dogs actually. So those are images for different cats and dogs. And I keep training the model, keep training, and after I train my machine to learn and understand the characteristic features of different animals in the image, of course, then I test by giving them a completely different, unseen image. Like if you look at the image of this dog, it's never presented on the data that I try to train the model on. And once I get this like a very completely new image, the model actually make the predictions. So that's the point. We have a very complicated structure of data, and then by our brain we cannot actually distinguish or analyze this data or find the characteristic features that hidden inside this data. So we ask the machine to help us in that. Well, so the what types actually of, yes please. صح. بس دي الاف اللي انا كنت بقول لك عليها، اللي انا y equals f of x, right؟ هنا very simple, so you cannot see the pattern.
بس قصدي ما اقدرش ان انا اعمل ماشين ليرنينج في البروسيس دي.
Of course you cannot.
عشان تبقى فاتي خالص.
ما لهاش اي لازمه. الماشين learning to help us on how to learn a very complicated patterns that our heads cannot realize. So that's but this is just like an example to show you.
In general I'm kind of some function.
Of course. If you can do actually, and if you can solve your problem with simple statistics, then there is no need for machine learning.
Even if it's pointless.
Exactly.
حتى لو كان ده pointless ما اقدرش اعمله.
Okay, so that's the point. You cannot use like a big tank to kill a small bird, right? So this is mindless. Another problem I'm going to discuss about that is what's called overfitting, overtraining, or lots of other problems that you cannot use actually machine learning, like a deep learning model, to analyze a very sensitive data. I'm going to discuss this.
أظن السؤال بيقول هل الداتا سيت بتاعت 1 زائد 2 1 زائد 7 is this data set with a pattern? Is there a pattern that could be statistically picked up on by the machine learning model وبعدين اديله 1 زائد 5 يساوي مليون ست؟ ولا اظن يوسف بيقول ان هو يعني فورمالي ماثيماتيكلي ما ينفعش نديله ماشين ليرنينج مش هينفع يعني.
لا يعني معلش.
يعني هو السؤال مش اذا كان ده مفيد ولا لا، السؤال
هل ينفع اعمل
هل
ده؟
فاندمنتلي يعني
صح. ما انا بقول له دلوقتي المشكله كالتالي، في مشاكل ثانيه ان انت تانلايز simple very simple data بالماشين ليرنينج.
حتى لو احنا ضربناه
المشكله في الفانكشن، ايوه الباترن هو اللي هي البلس دوت.
لا يعني هو في الاخر هيتعلم الفانكشن بتاعت البلس بدون ما اكون انا قايله طبعا.
بالظبط. هو لا انت مش انتوا لو انتوا فاكرين احنا كنا بنقول ايه؟ احنا بنقول المين تاسك بتاع الماشين ليرنينج ان هي تعمل لي ايه؟ احنا قلنا الواي equals f of x، صح؟ فاكرين دوت في المحاضره ولا ايه؟ اي ماشين ليرنينج وات ايفر الكومبلكسيتي بتاعت المشكله اللي انا عايز احلها او الكومبلكسيتي بتاعت الاف ديت هي ايه؟ ده اللي بتعمله الماشين ليرنينج. خلاص؟ طيب في حالتنا الاف هي ايه هنا؟
فانكشن
البلس.
رقمي
البلس صح كده. فهي دي الاف اللي الماشين ليرنينج موديل هيحاول ان هو يعملها ابروكسيميشن. وي كان دو ده. بس في مشاكل ثانيه هتقابلك اللي انا لسه بقى هنشرحها في حاله الديب ليرنينج، اللي هي زي مثلا اوفر فيتنج سمول سيت اوف داتا اند سو اون. بس في الاخر هو مش بيتعلم كذا حاجه. يعني انا مثلا زودت له الارقام هنا، لو انا زودت دوت من 1 لحد مليون، انا ما بزودش الاف، انا في الحقيقه بزود الاكس، صح؟ بس ذا سيم ايه؟ سيم فانكشن، صح؟ سيم اوبريشن.
بس على حضرتك لو مثلا حاجه زي كده قلت له 2 زائد 5 زائد 3 دي ما يعرفش.
ده ديفرنت ستوري، دي حاجه ثانيه.
ده ما يعرفش.
صح كده. احنا محتاجين بقى ساعتها نعمل ايه؟ نفكر of a new algorithm يقدر يديل with this problem. اوكي؟
بس هنا
بتكلم كواليتيفلي البروسيس دي مختلفه تماما عن البروسيس دي. احنا لما بنفكر فيها البرنسبل احنا لما بنيجي نعمل اديشن different عن ان احنا نبص على صورة حيوان وان احنا identify ايه هو.
طبعا
It's a very fundamental.
طبعا.
انا
انا
دي مش هقدر اعملها اصلا
يا
بالطريقة
جماعه انا جايب الموضوع ده بس كده just for illustration purposes.
على شكل عيال
That just for illustration purpose. Okay. So that one because when you, I mean, this is a learning, right? So this is a learning. So you can teach the logic for the kids, right? For a very simple pattern, very simple function, but for a very complicated function, we cannot do that with the kid. We need a computer with lots of CPUs and even cluster to find the pattern, right? So this is the comparison. This is why this is good. Huh? You have to calculate.
برضه هنا في الاف هنا انا كل مره بزود واحد كل مرة
صح.
بزود واحد. هنا لما اجي اقول اثنين يعني كده زي الخمسه هل هيفهم بقى؟
اكيد هيعرف لان هو ابروكسيميت الاف دي هي الباترن بتاعنا. This is very simple.
عارف.
لا هو بالتالي في باترن اللي احنا ممكن نعكسها يعني هو لا يعني انا خلاص.
Okay, so the machine learning actually it has like 3 or 4 different types. So the main categories of machine learning, we have like the supervised learning and semi-supervised learning and unsupervised learning, and the final one, which is the reinforcement learning. So the supervised learning, actually we are going to discuss this one and we focus onto that one. The semi-supervised for the supervised learning, we need actually a teacher or a tutor to teach the machine about the data. For the semi-supervised or the unsupervised learning, there is no teacher, no tutor at all. We give the data to the model and I ask to the machine and ask the machine to find some hidden information or characteristic information or patterns or if inside the data.
So in the supervised, the programmer say or whatever gives the data and then looks at the results and chooses different data next time, like iterating. That's what they do.
Yes. The idea here is that we add some labels.
Yeah. And the person decides what new data the machine needs to.
Exactly. So we guide the machine. But for the unsupervised learning, it's completely different. And for the reinforcement learning, it's about this kind of robotics, and then you design a robot to deal with the environment, and the robot actually learns from the environment. Like for example, if I give the model actually like a set of instructions, like previously, like very generic instructions, and then the model try to deal with the environment. So according to these instructions, if he make a positive things, then I give him 1. If a negative or did some wrong action, then I give him -1. And from this, it try to learn more and more and update the weights and update its logic. Okay, so example here. So for the supervised learning, so we have the labeled data or the data itself, and then we have the labels. So here we have what? We have a square, we have some hexagon, and we have triangle, right? So those are shapes, right? But still I have the labels of the shapes. And now every time I give the square to the model, to the machine, I tell the machine that this one is a square. So the machine actually learns that the square has 4 edges, right? Equals. And if I give a triangle, and every time I give also, if you see that the arrow, so I give the data together with the labels. So every time I give the shape of the triangle to the machine, I give also the name of that one. So every time the triangle have seen or shown on the machine learning model, I give the name of the triangle. So repeating that, the machine learning model actually learns that the triangle had the 3 edges. And once the model is trained, then I do the predictions. So I give it like 2 different stuff, and then I ask what is that shape is. Well, so as you can see, everything like the main part of the machine learning model actually comes in here and how to train the model. Not only this, how to choose the model that best solve your problem.
Example. So, like this is a classification. So we have two binary data set, one binary data set with two classes. Like we have the blue dots here and we have the red dots, right? And we want to create a model that can actually classify these two. On the other hand, here we have a points that has a continuous color map. So there are two different names here. So this can be categorized in different classes. Here, cannot be categorized in different classes because this is continuous. So if I'm dealing with the data, like it can be classified, like it can be put in different classes and different categories, this problem is called a classification problem. And if I have a continuous data set, this is called a regression problem. So that's the difference. And now, in this talk, we should focus on the regression problem. Okay, so how can we do that? First, when we train, we can assign a labels because, you know, machine computer does not understand names and does not understand anything. It's just only understand the numbers. So we give it like the blue points, we can assign a label to it like 0. And then the red points, we can assign a label to that one to 1. And then after we train, like every time we give the model the blue points with the 0, and every time we give the red points with the label 1, then the model actually learn a pattern here. And that pattern is the spatialization of the points into this, right? So if the points are above these thresholds in the x2 dimension, that means those are most likely being a blue points. If they are down here, then they are most likely being a red points. Okay, so this is the simple pattern that the model can learn, right? So that they are like a cluster or they have some separation. And according to that, the model actually now can predict the classification boundaries. It's just a simple line. It can be drawn here, such that the model actually can distinguish. And now after we test, now this is the training. So once we test now, if I give the model new unseen points, like a gray point for example, and if the point lies over here, then the model said, okay, this point's most likely being a blue point. If it lies over here, then the model output will be these points most likely will be red points. For the regression model, okay, so we have a continuous data, so we cannot actually assign a linear classifier between the two data because it's like a continuous color map. So the model actually can classify this by color map. So if the point lies over here, then it has a color, like for example, a black color with 0.1. If it's here, then a black color of 0.2, and so on and so forth. So here we can measure actually a probability between the 0 and 1. But here we also measure a probability, but this probability is either the points belongs to the first class or it belongs to the second class. So this is the major difference between classification and regression problems. Well, for the unsupervised learning, we have a different story. We don't have labels at all. We just have a bunch of data. And we don't know anything about this data. So one solution is that we give this data to the model, and then the model will try to look inside the data, try to find some different characterization or different features between the classes, and then at the end it can classify like a different the given data, it can be classified in different classes. And in this process, it's called letting the data set speaks to itself. So we don't have any control over that. Example. So obviously, unsupervised learning means no labels, right? So this is fact. For a classification problem, I give the model. This is the training. So I give the model a set of points that are in 2 dimensions. This points lives in 2 dimensions, x1, x2, right? And I give these points to the model. The model tries to learn a pattern of this data. So one can think of the pattern. What's the pattern again? Is the special position of the data, right? So those points are very, very near to each other. They're very close to each other. Then the model said, okay, those are one class. And the model gives
them a blue point. So the model classified these points as a blue points, which in this very close region. The other set of points that are clustered together, then the model said, okay, these are different, right? But why the model actually does not label those again with the blue color? Because the distance now, you see the distance is different, like, right? So here they have a large difference, a large distance between the two classes, but those classes have a small distance. Yes, please.
Did a human decide how far is too far and how is
No. The model classifies itself. There are some hyperparameter, depends on the model. If you use some unsupervised learning, then you have to tune it at the end. But obviously, like 80% no control.
Maybe a human decided that there should be more than one cluster.
That's true.
Okay, that's it.
Okay. For the regression, again, for the regression, unsupervised regression problem, we have like a Swiss roll shape of a gray point. And now the point, we don't have classes at all, right? So we don't have a blue and red class. But now the model actually tried to classify this according to the continuous color part of the very close data together. Well, so this is an example for the supervised learning versus the unsupervised learning. So for the supervised learning, we have a blue points and red points, and we train the model that, okay, those points have a label. This blue points and red points. And after training, the model actually will try to predict a classification boundaries that it can separate the two classes together. And now if you want to test your model and you give it a point, if the point lies over here, then it most likely belongs to the blue class. And if it lies down that classification line, then it belongs to the red class. On the other hand, if we do unsupervised learning, right? So we have a bunch of gray data. So there is no label. They're all the same. And now the model actually takes this data and try to find a pattern of this data, some different characteristic features that separates or be different from different set of points. And at the end, the model actually draw the classification boundaries, but in this case, the classification boundaries is not linear, it's kind of a circle around each class. So if the points in the test, if the point lies over here, then the prediction of the model will say, okay, this is a point which most likely belongs to the first class. And if it lies over here, then the model will say, this is a point which most likely belongs to the second class. And now the question is, what about those points? Right? What the model is gonna say in this case? No. Huh? Exactly. So it's a point that it does not belong to either the first class or the second class. These are points that they don't have a common feature among each other. So as you can see, they are far from each other, and also they are far from each class. So they are completely different points. Good. For images, another example. We have a supervised learning and unsupervised learning. For the supervised learning, we have a different images for different animals. Like we have a duck, different image of duck. We have a rabbit, and we have a hedgehog, right? And then I give the model some labels, and I wanted the model actually to understand some characteristic features of the duck image. So every time I give it the duck, then I teach the model, okay, this is a duck, okay? And if it, like for example, a rabbit or hedgehog, then I tell the model, this is not a duck. And when I do some prediction, when I do the test now, the model actually learns the features of each image, like the duck image and the other images. And now, for example, the model learns some features about the duck, which has like a long mouth, it has two wings, it has two legs, and that's it, right? Which is, when those two and these characteristic features is of course different than the other images, like the rabbit, which has a very long nose and so on. And now, as you can see, when I do test, I give a completely different image for duck that the model has not seen during the learning session. And once I give that, then the model think, yes, it has a long mouth. it has 2 wings, it has 2 legs, then this is most likely a duck. For the unsupervised learning, I don't give labels at all. I give images for different categories like duck, rabbit, hedgehog, and different duck, right? And then the model will start to dig inside the image and said, okay, this 2 data or these 2 images, they carry some common features, and those features are they have a common 2 wings, they have a common 2 legs. So I categorize the image which have a common feature together. So this is a 1 category. Then this is a rabbit, but this rabbit has a long nose, 4 legs. Then this is completely different, right? So this is another category. And for example, and also the hedgehog is completely different, right? So this is how the model actually, in the unsupervised learning, learn the hidden features of different classes. The last example is this one, which is a guy, a data scientist, will try to teach the robot actually. So in the case of the supervised learning, then he makes pictures of apples, and then he asks the machine, or the machine actually asks for help from the data scientist. So it gives the apple, and then this guy tried to learn, or the computer tried to learn, this is a banana. Then the data scientist says, okay, no, this is not a banana, this is an apple, right? So this is how we teach the machine. On the other hand, here in the unsupervised learning, there is no control from the data scientist. We do not do anything. We just give different images for apples and bananas together and ask the model to find a hidden feature inside. So every time it says, okay, this is something and this is something completely different. And from here, the model actually learns the different features are for the different classes. Well, so the supervised learning actually, we have a features, we have a labels, we give these 2 together to the supervised learning model, and then it tries to make a prediction, and the predictions now is nothing but it's most likely, because we are in a probabilistic model, so maybe it's most likely cat, most likely dog, and so on. So how it works in the details. So we give the features, like for example the images, to the model, and we have a labels here, right? So we give the image, and then we give it to the model. The model learn from this image, try to find some common features from this image. And now we have the predictions of the model. So when the model predict, we usually call this y hat or y dash, and this is the prediction of the model. But now how we make the model learn if the prediction is true or not? By minimizing the error function, cost function. That's true. So we have the labels, and this is how we supervise the learning of the machine learning. Okay. So every time we make the predictions, we compute the error function, and error function, it tells you how wrong the predictions of the model from the actual value or the true value or the true labels that you have. And once we actually compute this loss function, then we can update the weights. Like this here has a lots of free parameters, then we can give it like a new value for the here in this one, such that the prediction is a bit improved, and so on. We are going to discuss this in deep details. I think it's only like for examples. عشان باصص بيمشي صعب.
بس بعد لسه بدري، بس انت تدي محاضرة.
ما هو this parent session and listen that here
لسه فاضل كتير. انت النهارده فاضل كتير ولا؟ على العموم انت بتحس المبدأ الباصص هو بيمشي 4 وربع، بس انا مش عارف هو بتاعهم انتوا بيتفقوا الساعة كام اللي بياخدوا 4:30. طب لسه قدام
خلاص. عظيم
بس I can't guarantee انا بس ده مش ليا يعني. قدامك ساعة.
لا ساعتين، ممكن مثلا ساعة ونص ساعة. Okay. Okay. So as we said, for continuous data, then we are in a regression model, right? And in a classification data or in categorical data, then we are in a classification problem. So as you've seen in the introduction of the title of this talk, that we are going to discuss the linear and nonlinear regression model. So we have this kind of data which has some variation, but this data can be linearly described, right? So how can we? What kind of description or can we do for this data? So basically, the question is, we have the y and we have the x, right? And then we have this function, f. So the point is the following: if I give you a new x, can you predict y? Right? Yes, we can do that, but under one condition, that you know what f is, right? So in our case here, what do you think f is? Huh?
Almost as data. Almost as data.
Yes, you see that, yeah. Right? So you can find f. This is a line, right? And those are the points. And now I give you completely new points. So you just have this, and this is the prediction of the model, right? So we need the machine learning actually to tells us what is this, right? So this is the function actually. But now the question is that how many lines that we can draw over here that can fit the data? Infinite, right? So now the question is, how can we find the best fitted line to the data? That's the problem. So the best fitted line, the best fitted line give us the best predictions and the best accuracy. Okay. Well, so how can we find that? So we can actually draw this line, and now we have this y hat. It's nothing but the intersection and slope time the x. So now we have two parameters like b0 and b1. So as far as we change those parameters, the line is completely changing. So we want to find the values of b0 and b1 that best fit the line to the data. But again, how can we solve this problem? We can solve this problem by measuring the error. Like every time we change b0 and b1 and then compute the difference, this difference, right? Every time we compute this difference, and then we try to find the line that has the minimum value of the error between the data. But now the question also, how can we achieve that? Okay, so sorry. So how many like what kind of loss function that we can use in the regression model? So we have the absolute mean error, where it's nothing but the normalized 1 over m. The m is the number of the data set, just to normalize the output. And the y is actually the actual value. Y is this y for the points, right? And y hat is the prediction for the new points, like this is the y hat, right? So if I give you completely new point, point that you don't know about, then this is the prediction of the model. And always, all the time, you try to minimize actually the error between both of them. And of course, y hat is nothing but the equation of the line. We have also the mean square error. We just like square that one, and we have the root mean square error. So we can use all of them. But now the question is, how can we find again the line that can minimize the loss function? Okay, so now we take a step forward, and we completely change the problem on some optimization problem. So we have infinite number of lines. Both of them can fit the data. We need to find a line that can has the best fit of the data. So how can we find that one? By minimizing the loss function, by minimizing this loss function. But how can we minimize? We can minimize this loss function by what's called gradient descent method. So what is actually the gradient descent method? The gradient descent method is that we start with the
Still use these things? I thought خلاص بقى.
That's
This is
true.
ancient stuff.
That's true. But the main idea behind this, like the gradient descent,
Yeah.
but they have more upgraded under the cool, under this one. I'm going to discuss all
But
of
it's not very good for very high dimensions.
That's true. That's true. That's true. Nowadays they use atom commodity. So, but anyway, I'm just going to cover this.
Yeah, because I know that because you can't use it for more than 1,000 hours.
Of course, there are lots of even improved function, even more improved function. They also build down to. Okay, so what is exactly the method of the gradient descent? That we have the parameter, the free parameter that I just showed you, where are the free parameter of the line that they control how the f is actually, right? And now we have this one, and then we take step forward, and then we have the era. We take the gradient of the loss function with respect to the free parameter, and every time we update, we take a step forward to the minimum. So this is exactly how it looks like. So every time we compute or do iteration, like every time we iterate, and this is the number of the epochs. So if you remember in the last lecture, I told you that we need to iterate more and more and optimize, right? And this is how the optimization goes. So every time we do optimization by taking one step forward to the minimum of the loss function. And once we hit the minimum, then we know exactly that this fitted line can give us the predictions with the minimum error.
Actually, just to comment, the idea even goes back to Newton. You know that?
Yes.
Newton-Raphson.
That's true.
It actually
I
goes
heard
back to.
that. Yes, I
Yeah,
heard
yeah, I
that.
was thinking it goes back like 30 years ago. No, it goes back 300.
Yes, that's true. I heard that. Yes.
Newton-Raphson method. It's for he used it for solving nonlinear algebraic
Yes.
equations.
Yes.
Newton did that, but you of course did it by hand. But no, this is the same way.
Yes. So if you actually plot the error function, which is now the mean square error function versus the parameter p, then we find it takes this shape, right? So once we start with the random value of the b0 or b1, you most likely be here or there or even here, but we want to hit that one. So we need to iterate more and more, and every time we update the weights, the new p, by just doing this iteration more and more. But and this is you can find this in the codes. Okay, so by the way, all the results that you can see here, and you will see here, the codes relevant to that one, and the codes generates this plot. You can find it on the website. I don't know if Dr. Mahmoud is going to upload it on the website of the school or not, but you will find it anyway.
Did you send it? Oh yeah, you sent it to us. I'll tell you.
Okay. Okay, so as you can see, here we have this data at this point, and we just start with a random line, most likely this one. And when I compute the mean square error for this one, it's about 686, the value of that one. And as far as I keep going down, then you can see the value of the loss function start decreasing. And what that means? That means that the slope and the intersect of the line just changes. So it actually starts to fluctuate up and down, and it saturates to the value of the loss function or the error function that is minimum. And I can consider now this line is the line that has the minimum error and the line that can describe the data very well. Well, so there is one parameter that left over. We've not talked about the error parameter, right? And this is what's called the learning rate. So the learning rate, it controls the size of the step that we take, right? So for example, I can show you again, like here. When we take this step, right, when we update the weights, we multiply this by a number. So if this number is small, then the jump from here to here will be small. So if the learning rate is small, then we need to iterate for a long time until we hit the minimum. But what happens if the learning rate is quite high, quite large? That will happen. So it start to fluctuate, and most likely we will not be able to saturate at the global minimum of the loss function. So that's really important, that we have to control the value of the learning rate such that the descent is very smooth, and then we can hit the global minimum of the loss function. So as you can see, this is also a 3D. Like we have B0 and B1, and this is the loss function for two different learning rates. So if the learning rate is a bit large, then you find that lots of fluctuation. If the learning rate is even smaller, then we can have a smooth transition toward the minimum of the function, which is here. So you see how this one is fluctuated. That one, I think, hopefully it works. Oh, bingo, good. Okay, so what actually is this? So here, these are B0 and B1. This is the loss function, and there are three different learning rate values. So as you can see, as the learning rate, we start everything. So start everything from here, from scratch, right? And then you start descending this, right? So if the learning rate is very high, it's 7 to the minus 3, then it actually starts to fluctuate more and more. And then you have C here. This is the value, this is the MSE, the error function. So you can see the line actually here, which is this line. It always changes. It cannot saturate in the minimum. So in the minimum, so it always fluctuates, goes back and forth, and you see it cannot converge. Maybe if you train this for a very long time, it can converge, but I'm doubt about that. So you can see here how the effect actually of the learning rate. And this learning rate, it's a hyperparameter, means that it's a parameter that the user should fix its value. So you should have to try actually different values for the learning rate, and the learning rate that gives you the best accuracy, you take it.
I've got a question.
Yes, please.
Is there a systematic way to find out the best learning rate for?
No, it's by experience. No way. No. Okay, so
Ya Allah. Make a machine learning model
to predict the learning rate. Yeah, I'm going to discuss a bit on lecture number 4 when we deal with the deep learning about how this learning rate actually, it's not fixed in some modern, like what Dr. Ahmed mentioned, about very modern optimization algorithm like XG Boost, Atom Optimizer, and so on. So it's not fixed. When you use that, it's updated. But we are going to discuss this in lecture number 4. Okay, so that was about the regression continuous data. What about categorical data? Right. So we have a data that has two categories. Like one is clustered around 1 and one is clustered around 0. And now the question is, can we do that exactly the same as we've done in the case of the linear continuous data? No, we cannot. Because if you want to fit this line, this is how it looks like. You will never, ever be able to fit this line. So we have to think differently. So we need a source of nonlinearity. And this nonlinearity is actually what's called sigmoid function. So we can fit this, instead of fitting this to a linear line, we can fit it to a sigmoid function like this. And now the question is, can we use the other loss functions that we mentioned earlier, like can we use those functions to minimize or find the best sigmoid function, or the sigmoid function that best fit the data?
Yes.
No. But thanks for your try.
عشان لو عملنا كده هتبقى اوفر فيت يعني.
No, it will exhibit more local minimum. That's the point. So if you use the mean square error, absolute error, root mean square error, then it will gives you two minimum, right? So one minimum here, one minimum there. So even that functions, error function we cannot use. So we have to think of something different. And that one is called cross entropy loss for the function. And this is how the entropy loss function looks like. And actually the entropy, it's very known, right? And also from the information theory, it's the entropy actually, it tells you about the uncertain event to take place. This is from the information theory. And the entropy is the log of 1 over the probability. So you can think of it, it's the uncertainty or the noise. So measuring the entropy, it means that you measure the uncertainty of your predictions. Like how far my model is away from the right answer, or how many mistakes that the model is doing. And of course, as we have the entropy is log 1 minus of the probability, then we could always have the minus sign here, and then we have the log of the prediction.
Probability of the model?
Sorry?
Probability of what? Probability
The
of
prediction.
model?
Yes, the prediction.
Of the model.
Yes, true.
So this is a Bayesian probability? Or
Sorry?
Bayesian probability? of
Ah,
the
no, no,
model?
no, no,
So
no.
it's not like that. So
No,
what
it's
is
the probability. This one. It's the probability.
probability of what?
This one.
Of the fit?
Exactly. So this is the y hat.
Ah. Okay. So. So entropy is usually lack of knowledge. So it's how many parameters are missing or something. So entropy is usually a lack of knowledge. So this is like right in this James entropy information.
That's yes. Okay. Yeah, but it also tells you about the uncertain, like how the uncertain events take place in the data, right? So it also measure of the uncertainty or the error that you may have.
So not of the error usually,
Like
no. It's of the missing details.
That's
So the missing details is of what you don't know.
Yeah, exactly.
Is what is not necessarily an error.
Okay.
Ignorance.
Okay. Yes, that's true. That's
Of
true.
what you know.
Okay.
No, because this is also in dynamicals. I know information entropy because it's connected to dynamical entropies, Kolmogorov entropies,
Yes.
and James entropy, which is a measure of information you don't know because of ignorance.
That's true. Yeah.
So basically missing parameters.
Exactly. Or our lack of knowledge, basically.
Yes,
So we
exactly.
this. Yeah. So we need to overcome.
Okay,
it.
so yeah, right.
So in here, you could always have this negative sign, and then we could have this what's called the categorical or the binary entropy loss function, which is the y. This is the true value that we have, like this, the exact y value here, and y hat is the predicted by the model, and then we add another.
Sorry, how many parameters do you have in this model?
That's 2, I think.
So so entropy is really not that well defined, is it? So in that sense. Because you have a probability in the model.
Yes.
That's right. Okay, right.
So we have this the y, the first term, and also 1 minus the y and 1 minus the y hat. So this term actually it makes the binary cross entropy or the categorical cross entropy. And as you can see now, we have 2 lines, right? So these 2 lines actually cross each other in 1 minimum. So now we hit the global minimum. Oh, now we can find the global minimum. Unlike the other one, which has 2 local minimum and the minimum and 2 local minima, and then we cannot find actually which one is the global one. So dealing with the categorical data we need to use the cross entropy or entropy loss function. And if you deal with the continuous data, like in the regression problem, then we can use the mean error functions. Okay. Well, so now we come to all of what we just discussed was about the linear problem. But now we could have some nonlinear problem. Of course, also we cannot feed that with a line, so we need to add more degrees of freedom to fit this data to the line. Okay, so how can we add this? Another way, instead of using this simple sigmoid function, we could have a binomial function to fit this data. Of course, y hat, it's a polynomial of degrees 2, so we have a w1x1, w2x2 plus the b0, which is the bias. And now the question is, how many powers to fit we can find or we can define in the polynomial model to fit the data, right? So this is also another question. I can add here, right? So now what is exactly the power that we can have? for the number. Okay, so you can see that one. Okay, so what's that about? Here, this is the maximum power. It counts the power. It means that we have more and more powers here. We add, and these are actually the loss function. But those two lines actually, one for the train and one for the test. So here we have the training. Here we have the training data. The loss function is quite high, and as far as we keep iterating, you see the loss function is very nicely decreasing with the iterations, with the number of iterations. But also the test is also, when we test the model for the nuancing data, it's also decreasing. But at some point here, there's something strange happens. Look. Here. So it nicely, and then it tries to fit everything in the data. So now the line, the classification line, or the line that describes the data, is no longer describing the data itself, but also describes the error in the data. So if there is uncertainty of the data, like for example, this is the trend of the data, right? Those very far away points are like uncertainty, noise in the data, right? So the model now starts not to fit the data, but also start to fit the noise into the data. And this is why it makes a completely wrong prediction. This is the answer for your question at the beginning, okay? Got it?
This is overfitting.
This is the overfitting. So even if you have a very small data and you try to make the model learn more and more and more, and you have more free parameters to tune for a very simple problem, then the model is going to overfit. It learned a completely different stuff. And here's the rule. When using a machine or a deep learning model, the number of the trainable parameter should always be less than the number of the given data or the problem under the one, like the dimension of the data and the problem that you want to solve. Well, so again, this is overfitting. So like here, we don't know actually where to stop, where exactly the best region to stop, right? So we have here, when we started the iteration, then the model actually also give us a large error, like here, right? This is large. Also, this is large, right? So we need to stick here. So we have here, there's like a high bias. What do you mean by high bias? Look again. Look, it's naively described the data, right? So it's like a straight line or like a convex shape, something like that. So this is what I mean here by high bias. And if you keep training and fitting the data more and more, it will be like a high variance. Now your classifiers will exhibit some high variance behavior. That means the model, the classification of the model actually learn the noise into the data, not only the data, and then it has more and more variance on its shape. So what to do? We need to stay here. Okay. So how to solve this problem? We are going to cover this in the future lectures. How to find the best fit. The sweet spot. Good. So this is also how the overfitting looks like. So when you train the model, you have like a Ferrari car, a very nice car, very fast car. But when you test the model, this is how your car looks like. حرفيا انت بتخش في الحته العربيه بتاعتك. لانه وانت بتtrain a model, then you have a very nice intuition that you have a very good accuracy. You have a very good predictions, right?
If your penalty function is a standard chi-squared with error bars and so on, then it's fine. I mean,
This is for the training.
No, but I mean the training has a penalty function, right? I mean
The error function.
Yeah,
Those
the error
function.
function.
Yes. This is the function that you minimize.
yeah. So your function should contain the error bars, the errors in the data, to know it.
No, usually no. This is
Not
included
your-
into the prediction.
I
No,
know.
I had.
No, you do like the least squares, divided by the errors so that you do the chi-squared so it's near 1.
Okay, yeah,
per
but
degree of freedom.
yeah, but most likely
So that you can,
that's true, but most
that's
likely
what you do in normal physics.
yeah, but most likely in the data in the real life, we don't know where exactly the nodes. We don't even.
So you don't know error bars like in physics.
Exactly.
Ah.
Because here, this is not physics. This is a computer science course.
Oh, but then maybe you don't. So you don't have estimates of
Exactly.
what
Of
noise
the error.
is.
Yes.
But you don't get that in physics also. Then you need to model background.
That's true, but in the real life, we don't have even
You
how to
don't
do
have
it.
model background.
We don't have a model. We use a machine learning to model,
Yes.
but we don't have a background, so we cannot estimate
But
it.
is there a real life outside of physics?
Sorry.
Is there real life outside of physics?
I'm talking about. Okay. Okay.
بس هو لو في حاجه زي كده ممكن نحط السترينز على السيستم. لو انا عارف، لو انا عندي معلومات عن الداتا شيرين، فاحط السترينز بحيث ان يعني احط الشروط بحيث ان هو
ده حقيقي.
يمشي عليه.
دي حاجه اسمها regularization model او regularized model. اشرحها بعد
So you want a method independent of the estimate of the noise?
Of course, because most of the time we don't know what's going on. This is how your data, like when you train, but when you test, you got a completely wrong answer, and a model, you find that your model is doing nothing, right? Okay, so how to solve this problem actually, right? So we have this one. This is like I have a bias. Like this is the classifier. So the red line here is the line that the true line or the line that best fit the data, right? We know the line. Sorry?
That normally I do not know.
Exactly. So we know, but we know this line because this is simple data, right? Okay. And we wanted to train machine learning model such that the prediction of the model can estimate this line. So if you have a small degrees of freedom, like the power of the polynomial, right? Then you have this classifier. Because here also we said this is the complexity of the model, like how many fit parameters it could add. So if we have a small, like a polynomial of degree 1, then you have a large bias. And this is exactly this area here, right? So the model is unable to describe your data well. Adding more degrees of freedom, then the model actually is able to fit the data. So this is degrees polynomial of degree 5. Adding more degree to the polynomial function, then it starts to fluctuate, and now it fits every point in the data, and we don't need that, right? And now the question is, we want to construct a loss function that forces the model to remove the power above the best fits, because also we don't know, right? We don't know which polynomial model that we use, right? So we can use like we start with the model and then we constrain that model. So this comes in the regularized regression models. So maybe tomorrow I can keep with this regularized model. Or
Yeah, if you want. I mean, it depends.
طيب نكمل ال regularized model next ولا I don't know. معرفش ممكن
على حسب هنسال ولا مش
هو
هنسال.
هيفيد ضغط عليك كمان خالص.
اوكي good.
عماد انت لو تبتدي تفاصيل ديتيل يمكن احسن من اول بقى بكره يعني.
لا ده هم it's just a couple of slides.
خلاص جو.
ما خدتش بالي. Okay, so regularized function. So what is exactly the regularized function? So this is the what's called lasso model and ridge models, and these are very known models in machine learning if you heard of them. And it's called also L1 and L2 regularization models. The point is the following. This is the absolute mean. I forgot this one. Should be this one. Okay, so this is the absolute mean error function, and then we add a penalty term, right? So this is the penalty term. It's term of the powers of the polynomial. So as far as you increase the number of the powers of the polynomial, then your loss function increase and never decrease, right? So the point is that to decrease the loss function here, then you need to minimize this term. So now we penalize the source that makes the model to overfit, as you can see here, right? Here, we don't need that. So here it's a degree of, this is binomial degree for 15. So we need to stick to the number of 4, but we don't know, right? So we can add this term to the loss function such that if we increase the number here, the loss function also increased. So
But how do we know that it's due to the noise, not due to anything?
We don't know.
else? Yeah.
we just add this.
Oh, no.
This is a hyperparameter that we have to set each time by hand. And then at some point, if this loss function hits the minimum, like the
So
zero
Lagrange
minimized.
multiplier.
Exactly, like a Lagrange multiplier.
So Lagrange, okay.
Exactly, this is a Lagrange multiplier.
Okay, and you minimize with respect to the order of, in this case, order.
Exactly.
Okay.
Exactly. So
Again, not very new. But
this is very, very old.
yeah.
Yeah. This is very ancient technique, and this is still a machine learning model. So this is, if you remember this
So
chart.
from 17th century to 18th
Yes, that's true.
century.
Yeah.
Okay. You still have a couple of hundred years to go.
Yes. So if you think about this chart, so we have the artificial intelligence, and then we have the machine learning. Down to we have the neural network and the deep learning. So those are machine learning models. They are very shallow models. And okay, so there is L1 and L2. Also, you could have the square. So now my question for you is, when exactly was that the question? Exactly. In which analysis problem do we need to use lasso overage regression?
What?
Lasso overage. Like in which kind of problem that we won't actually, or we might use this one over this one. So both of them are exactly the same. Both of them are penalizing the increase of the polynomial power, right? But one is only without the
So
square.
tell, maybe you should, if I forget, you should tell Mahmoud to put the stuff on the web so that they can.
Okay.
Because I mean, they need. For those
Yes.
who don't know, they need to look at it carefully.
Okay, yes. So, yes, please.
Just looking, they're identical. The rich model punishes it a lot more because of the square. So it depends if I expect to have a lot of polynomial terms, and I don't want it. Like it really depends on my general estimate.
You are quite close, but not that. Yeah, just a little bit close. Just think of it. Yeah.
I think the first one, the last model, will decrease the error, decrease the cost function if we put negative values for the omega.
No.
Right?
No, this is
There is absolute
Wait, no, this is just the structure of the function.
So
We don't add any zero, any negative values.
omega 1 cannot be negative, omega 2 cannot be negative.
Like here, like this one.
Yes.
Oh, sorry, this is the.
ولا في absolute value هنا.
No, this is the absolute value.
Absolute value.
Yeah, not the absolute value, but this should be positive all the time.
Omega
So
is
when you deal with other data, then this term you keep it like positive by adding some absolute or something. But this is no negative hint. Okay, so please think of that one like as a simple homework.
Okay, thanks a lot. خلاص ولا لسه؟
خلاص.
Thank you very much, very interesting. طيب اللي عايزين بكره اللي يحب يجي ده optional يعني we can discuss معايا مع الناس التانية أي أسئلة general questions queries complaints اعتراضات